All right, so we move on now into section 10.5, parametric surfaces. And the book says it very well, the way it states. Let me just find the book here. Hold on. One moment. I have a few too many windows open. There it is. Okay. So, all right, we saw surfaces before back in section 9.6, but those surfaces are where we could write functions of two variables. So like for instance, like if I go to the whiteboard here and show you, so you can have, for instance, a function of x and y. And let's say that equals x squared plus y squared. Now that's a surface. And that surface you probably recognize as a paraboloid. Okay, and hold on, I just want to make sure I'm spelling that right. One moment here. Paraboloid, it's paraboloid. Yes, yes. So the idea is the function of x and y you can represent by z. And if z equals x squared plus, one moment. Now that's how it's spelled. This is an O. This is an O here, paraboloid. That's how it's spelled. Yeah. No problem, Yeva. So, okay, this is a surface, and we know that this surface here would emanate from the origin. It would go up. You know, it would go up along the z-axis here, and that would be the surface. But what if you had a surface like this? What if you had x squared plus y squared equals 4? What kind of surface is that? X squared plus y squared equals 4. Well, so in 2 dimensions, that Ashish, in 2 dimensions, this is a circle. But in 3 dimensions, well, a sphere would be if we had, whoops, now hold on, what happened there? Hold on. Whoa, hold on. There we go, okay. A cylinder, that's what we want. That's what we want. That's right, Simon and Iberdeen. This here is a cylinder. And you see how you can't write this as a function of x and y. There's no z, for instance. There's no z variable for the cylinder. But yet it's a surface too. So we want to be able to represent all different kinds of surfaces using an approach that will always work. Now the sphere, Yeva, you mentioned about a sphere centered at the origin with radius 2 would have an equation of x squared plus y squared plus z squared equals 4. But yet there's another type of surface. It's a surface, but we can't, you know, like z equals f of xy. We can't take a sphere and write it in this form. So we want to have a very general approach that can help us analyze these kind of surfaces. Okay. By the way, EB, is EB okay? one of my students? Is that okay? I want to make sure.
I usually call me IB.
I usually call you IB.
Yeah,
Is
IB.
that
IB is fine.
IB is good? Okay, IB. Excellent, excellent. We'll go with that. All right, so let's head back to the book here. Let's head back to the book. So how are we going to take on this task? Well, okay, what we do is this. In much the same way we describe a space curve by a vector function r of t of a single parameter. Now what I'm doing, I want to make sure this is what I'm talking about right here. Okay, so in much the same way we describe a space curve by a vector function of a single parameter t, we can describe a surface by a vector function of two parameters u and v. So any space curve traced out in space can be written as a vector function of a single parameter. But if we want to trace out a surface in space, we can express it as a vector function of two parameters. Okay, and there's the format there in Formula 1. And you notice that the components, the x, y, and z components are functions of those parameters. Okay, in other words, this is a vector valued function defined on a region D in the UV plane. So the x, y, and z component functions are functions of two variables. Now, so, these are your parametric equations for your surface. In order to describe the surface, you need parametric equations for x, y, and z. And if we were to look at this geometrically, figure 1 shows what we're doing. So you see figure 1 has the UV parameters. Okay, so like parameters u and v, like if you think of the variables x and y, you can have a plane, right? You have a plane with an x-axis, a y-axis, and all the coordinate x, y coordinates. Well, parameters u and v, you can have a u-axis and a v-axis and coordinates uv. And these coordinates uv are different values of the parameters, and they form a region D or domain. And based on the values of the parameters u and v, we define a vector function r that is a function of u and v. So the vector function r consists of three components: an x component, a y component, and a z component. It's just each of those components are functions of the parameters. So if you give me a value of u and you give me a value of v, I'll have my components x, y, z, and I can draw a vector. Now imagine if you let u and v change. You let it change throughout the domain there that they show on the left in figure 1. Well, that's going to correspond to different vectors, and you're tracing out, essentially, you're scribbling out a surface S in space. That's what you're doing. Think of like taking a crayon. This isn't probably, but the way I think of this, that vector function r, I think of a crayon, and the crayon, as u and v change, the vector function r, which is the crayon, it moves, and it traces out a surface S in space. So this is a very elegant way to represent a surface S in space. And let's go ahead and look at some examples here. Okay, so we'll look at the first example. Hold on. Okay, so first example says identify and sketch the surface with this vector equation. Okay, so look at your components. You have 2 cosine of u, that's your x component. The y component equals v, and the z component is 2 times the sine of u. So as u changes, well, let me ask you this. Are the x and y components, you know, x is 2 cosine u and v is 2 sine u, are they related at all to the component, the y component, which equals v? Is there any dependency? Or are the x and z components affected? Do they act independently of the y component? What do you think? That's right, Marina. They act independently. Um, let's see here. So let me go to the whiteboard. Hold on. Talk about this. One moment. Okay, so we're looking at example 1 here. Okay, so let me just write down this. This is a vector function of 2 variables, 2 parameters. Okay. And it's going to trace out some surface in space. So we have our x component, our y component, and our z component. Okay, now let's note something here. If you take x squared plus y squared, okay, you'd have 2 cosine u quantity squared plus 2 sine u quantity squared, which is 4 cosine squared u plus 4 sine squared u. We can factor the 4 out. And what's cosine squared of u plus sine squared of u equal to? 1. Good. Good, Yeva. So that equals 4. So whatever this surface looks like, okay, the x and y coordinates, the sum of the squares of those coordinates equal 4. When x squared plus y squared equals 4, oh, I have a little error here, though. I have a little error. It's x squared plus z squared, right? So whatever coordinates are on the surface, okay, whatever x, y, z coordinates are on the surface, whatever points are on the surface, for all of those points, x squared plus z squared equals 4. Okay, so, all right, so we have x squared plus z squared equals 4. What is that? X squared plus z squared equals 4. What does that represent? What kind of behavior is going on here? That's right, Simon. So think of it like this. Think of it like this. Let me see if I can. Think of it like this. So for this surface here, okay, could y equals 0 and x squared plus z squared equals 4? Yeah, somebody's mic's on. Thank you, Brian or Yavin. I forget. I don't know who it is. Maybe Brian, is your mic on? You think? Or it happens. No big deal. Somebody's mic's on. Maybe I don't know who it is. A moment here. Okay. Can you all hear me okay? Give me a thumbs up. Okay, good, good. Wonderful. Thank you, Yeva. Thank you, Lexi. So let's consider, thank you, Matthew. Let's consider this situation where, you know, y equals 0 and x squared plus z squared equals 4. That would go with u equals something, and, well, I want to say this the right way. I want to say this the right way. Could u be between 0 and 2 pi, and could v equal 0? So we agree that when x squared plus z squared equals 4 and y equals 0, we have a circle. We have a circle at y equals 0. Okay, hang on, Brian. Hold on. One moment. One moment. Brian, I'm gonna remove you from the session, okay? Just come. Hold on. I'm sorry, everybody. Let me deal with this. It happens. It happens. It happens. It's nobody's fault. Nobody's fault. It's just part of remote teaching. One moment. Okay. Sorry. Okay. So we know that for this space curve, by virtue of this here, that x squared plus z squared, I'm sorry, we know for this surface, okay, and the surface, right, consists of coordinates, points, x, y, and z, you know, but for every one of those coordinates, x squared plus z squared equals 4. So x squared plus z squared equals 4 and y equals 0. that we recognize is that that's a circle at y equals 0. So essentially, that's a circle in the xz plane. And it is on our space curve because you can go from, to trace that circle out, you can go from 0 to 2 pi, that's allowed. And then if we're demanding that y equals 0, then v has to equal 0. Now, if we had, for instance, y equals 2 and x squared plus z squared equals 4, those points on the surface would correspond to the variable u, the parameter u, being anywhere from 0 to 2 pi, because that would trace out a circle. And what would v equal? What would v have to equal if y equals 2? What would the value of parameter v equal? That's right, yeah, it would equal 2. So now here we have another circle. This here is a circle at y equals 2. So you see, basically we can view this vector function of two variables as tracing out a surface composed of circles. And the circles are vertical circles, either like parallel to the xz plane at different distances along the y-axis. So if we like put this information together, okay, if we put this information together, this is going to be our surface. Hold on. Yeah. This is going to be our surface. You see that? You ever see like I think of a good example. You ever see like how many know the Mission Impossible movies? The Mission Impossible movies. Like where they gotta make a face with that machine. How many have seen that? All right, Mary, Aura, Samuel. Well, any of the ones, but like usually the first 3 or 4 of them. Remember, they had to make they'd have to make a fake mask. They had to make a mask, and so that machine has a device that scratches out a mask, a fake face. That's right, Samuel. That's what we're doing here. We're scratching out a surface, just like in Mission Impossible, how the device scratches out essentially a face. That's what this reminds me of. Okay, so if you want to represent a cylinder with radius 2 that's parallel to the y-axis, whose y-axis goes through its center, the parametric representation of that is given here. So you see, we can't write a cylinder as a function of x and y. We can't say our cylinder, z equals whatever, and get a cylinder. We can't do that. But using vector functions of two variables, we can generate a cylinder. Let's look at another example here. Let me go down a little bit. Okay, let's talk about a plane. Okay, so you dealt a lot with planes in section 2.9.5. One moment. Okay, thank you. So let me highlight the instructions here. So we want to find a vector function that represents a plane that passes through a point with a position vector that contains two non-parallel vectors A and B. Okay, so how would we represent that? Well, here in figure 6 is a picture of a plane that passes through, that contains the point P sub 0. And any point in that plane is a linear combination of the vectors A and B. So you see the vector function that represents the plane is equal to this R sub 0. R sub 0 is the vector function that goes from the origin out to the point P sub 0, plus then any linear combination of vectors A and B. That will trace out a plane in space. Okay, and so the parametric functions or parametric equations for the plane are given by x, y, and z as shown here. Okay, the more examples we look at, I think the better. Let's look at another one here. Let's look at another one. Okay, we have here a sphere. A sphere. Okay, one moment, class. I have a student trying to log back into class. One moment. Okay, so here's this sphere. Okay, a sphere centered at the origin of with radius a. Now, what would the parametric equations be for that sphere? Well, in this case, you know, again, the variables u and v are those are parameters, but you could also use angles phi and theta as the parameters. And if you describe your parametric equations here this way, so the radius a is some number, that's not a parameter, but the values of theta and phi are your parameters, and x, y, and z, those are the definitions of the equations, the spherical equations for x, y, and z that you learned back in section 9.7. Okay, if you just, you know, if those are your parametric equations, then your vector equation is what you see here. And notice that phi has to go between 0 and pi, and theta has to go between 0 and 2 pi. If you allow that, then the parameter domain is what they showed here below. Okay, for your phi, remember, goes from 0 to pi, and theta goes from 0 to 2 pi, and you're letting theta and phi vary all across that domain. And if you do so, you will trace out a sphere. So you see in the sphere, you see how you see that red circle on that sphere? Give me a thumbs up if you're noticing that. Yeah, yeah. And you see how it says phi equals c? That means phi equals a constant. So all the points. Okay, nice to have you back, Brian. I'm glad. Okay, excellent, excellent. All the points on the on that red circle, uh, theta will vary from 0 to 2 pi, but the angle phi is going to be some constant value, maybe like 45 degrees. Phi equals pi over 4, for instance. Now, on the other hand, you see that blue vertical circle on the sphere that they trace out. That's called, these are grid curves. These are grid curves that they're showing you here. Phi equals c is a horizontal grid curve, and theta equals k is a vertical grid curve. So for theta equals k, they're letting that's that vertical blue grid curve. Give me a thumbs up if you see that in the picture. I'd like to make sure this is example 4, figure 7. Good, thank you, Angela, Yeva, Narina, and Matthew. Good, good. So you see, and Alberto, thank you. Thank you. Let me see here. Hold on here. One moment. Arian and Brian, wonderful, wonderful. So you see, you're letting, and Logan, excellent. So you see that you're letting theta be a constant. Thank you, Ashifa. So there, maybe, like, what angle do you think you're letting theta equal? Looking at that blue grid curve. So phi goes from 0 to pi. Okay. What theta is being shown there? I agree, Lexi. Maybe about 45 degrees, pi over 4. So you see, the point is when you hold one of the parameters constant, it traces out a grid curve, and that's what you see up there in the region D, where phi can go from 0 to pi and theta can go from 0 to 2 pi. They're drawing two lines on that domain. One is where the vertical line, where phi equals c, a vertical line segment, and that corresponds to the horizontal grid curve that you see, that red grid curve that you see on the sphere. And then if they let theta equals k, that horizontal line segment, that would trace out then the vertical grid curve that you see on the sphere. Remember, when you hold one of the parameters constant, you have a vector function of two variables, of two parameters now to trace the surface out. But if you hold one of those parameters constant, you now only have a vector function of one parameter, and that traces out a space curve. A space curve is a grid curve. That's what they're showing you here in this example of 4. Are there any questions on this so far? Okay. Okay. Well, let's look at another one. Let's look at another problem here from the book. And then I have a problem I'm going to do with you, but here, okay, in example 2, let me see, I don't want all this highlighted. In example 2, they want you to use a computer algebra system to graph this surface. Okay, so this is a more complex surface, but actually it's not that difficult, because so remember, if you hold one of the parameters constant, you're going to get a grid curve. So let's say, for instance, that you were to hold the parameter v constant. If you were to hold the parameter v constant, so like if you were to hold that constant, let me see here. Let me just go to the whiteboard actually on this one. I think it's worth doing. So this is example 2. Okay, so example 2. I don't know why I did that. Example 2 from section 10.5. Okay, so the x component is 2 plus the sine of v times the cosine of u. That's the x component. The y component is 2 plus the sine of v times the sine of u. Okay, that's your y component. And then the v component is u plus, I'm sorry, the z component is u plus the cosine of v. That's the z component. Okay, so let's say that you were to let v equal 0. You would have r of the parameter u only because v equals 0. Now that would trace out a grid curve. And what would that grid curve look like? Well, so you'd have 2 plus the sine of 0 times cosine of u, 2 plus the sine of 0 times sine of u, and then you'd have u plus the cosine of 0. We know the sine of 0 equals 0. So we'd have 2 times the cosine of u as the x component of this space curve, 2 times the sine of u as the y component of the space curve, and then we'd have u plus 1 because the cosine of 0 is equal to 1. And, you know, we knew the sine of 0 was equal to 0. So here's our space curve. Here's our space curve, right? Here's our space curve when we let v equal 0. Two cosine of u, 2 sine of u. What kind of behavior would that be? What would the space curve be doing with respect to the x and y? A circle. So it's going to be, that's right, Lexi. It's going to be moving along a circle of radius 2 in the horizontal direction. Okay. Now one moment here. One moment. Let me just. That's right. That's right. And what's happening in the z direction? The z direction, you have u plus 1. So as u increases, what's happening to this space curve? Is it going up or down? It's going up. So what would this space curve be if that's right. If it's horizontal space curve is moving in circles, with respect to the, like horizontally, but it's going up at the same time. What describes that? Well, if we let, you know, if you could be just, so they're not putting any restrictions on I want to say this the right way. If I want to say this the right way. So, do you recognize this as a helix? Yeah, that's all. So like this is a helix. This is a helix. And by the way, if we were to let V equal, let's say V were equal to pi over 2, then you'd have R of U comma pi over 2. Okay, that would equal, well, that would equal 3 times the cosine of U, because the sine of, you know, the sine of pi over 2 is equal to 1. Okay, so we'd have 3 cosine of U, 3 sine of U, and then we'd have U plus 0, because the cosine of pi over 2 is 0. Okay, so this would also be another helix. This would be also a helix. Okay, so for different values of V, we generate space curves that are all helices. The grid curves are helices. And if you put those helices, that they're helices that go up, they move upward, but horizontally they act as circles. They move in circles with different radii. This helix here has a radii of 3, whereas the helix where we let V equal 0 has a radius of 2. Okay, so now let me just see here if I can mention anything else. What would it look like putting all these helices together? What it would look like is, hold on here, it would look something like that. You see how on figure 5, and by the way, they are letting the domain U go from 0 to 4 pi, and they're letting the domain U goes from 0 to 4 pi and V goes from 0 to 2 pi. They mentioned that. But you see, like, remember when we let V equal 0 and V equal pi over 2, that traced out 2 space curves that have different radii. And if you look at the grid curves where V is constant, okay, you see how you get helices? You get helices with different radii that move upward. And if you put all the helices together, it traces out this pretzel-looking surface. Does that make sense? Now we're going to use a computer to get this figure, but I'm just saying that the grid curves where V is constant, that they show in the picture in Figure 5, do you see how the grid curves, if you follow the grid curves where V is constant, there's two grid curves there, and they're tracing out two helices. Do you see that in Figure 5? I want to make sure you're okay with that. Okay, so I'm not getting too much response here. Let me go back to the whiteboard here. Okay, so this is the example 2 that we just saw the picture of. We saw the surface. We agree that this is going to trace out this vector function of 2 parameters is going to trace out a surface, right? It's going to trace out a surface. But you can think of a surface as combining together a bunch of space curves, right? I'm trying to think of that. What is it, that cheese? It's called stringo cheese or something, where you have like cheese, and as you can peel off certain pieces of the cheese, and I'm trying to think of something that you peel off, like certain pieces, and I mean, I think I have it right. So stringo cheese comes in a surface, and if you peel off pieces, you're peeling off like space curves, but all the spacers curves together form the piece of cheese. I don't know if that's a good analogy or not, but the point is, what you're doing is, the way you can think of this uh, uh, surface being traced out by this vector function of 2 variables. Hold the one variable constant, let it take on different values, and for each of these values you generate helices, a helix of a different radius. If you put those helices together, that's going to trace out a surface that looks like this. So I think if you do some practice, it'll help you. There is a MATLAB program for this example. If you go into your MATLAB programs, let me just see here. Let me just bring it up. Okay, if you go into your MATLAB programs, okay, you see there's a MATLAB program for section 10.5, parametric surfaces. This MATLAB program will draw the surface that you just saw in Figure 5, okay, from section 10.5. So go ahead and click on the link and open up the program. And when you open up the program, copy and paste that MATLAB program in the editor for MATLAB. And when you do that, let me just one moment here. So I'd like everybody to try this. Are you getting this? Is this what you're seeing? This code. Okay, Yeva's seeing it, Logan's seeing it. Wonderful, wonderful. So this code will graph that helicoid. That surface is called a helicoid. It'll graph that surface in MATLAB. And what you do here is you know, the code is such that you define your symbolic variables, u and v. It's just sims, u and v. And then x, y, and z are your parametric equations. And then you're going to use easy surf command. And I'm restricting the u to be from 0 to 4 pi and the v parameter to go from 0 to 4 pi. Okay, so we can copy and paste the code. And when you do that, okay, when you do that, how many of you are getting the surface? Good. Whoops, hold on. Did mine disappear? Hold on. All right, so it's kind of blocking me a little bit, so I can't see who's seeing it, but that's excellent, excellent. And then, you know, you can view it, and you can go to tools. You can go to tools, and you can rotate it. You know, you can rotate it. And you know, the way MATLAB has it is, well, you see, like here, the x-axis is good. You know, it goes from negative to positive in the forward direction, but the y-axis is like reversed. So you can flip things, and try to get it, you know, going the right way. And it takes a little time to do. I will tell you, it can take a little time. But you know, just play around with it enough. There we go, there we go. Yep, that's it, that's it, that's it. How about that, class, huh? So the x, y, and z axes are exactly like what you're used to. What you're used to. And I kind of wish MATLAB by default would have the axes go like that. But at any rate, just go to tools and rotate, and you'll get there. Okay, are there any questions on this? Okay, okay, great, great. All right, so what I'd like to do, I would like to give you a 10-minute break here till about 7:30. And let me go ahead and make the section 10.5 assignment available for you. Let me go in. So the assignments are deactivated. I'll activate them all after class. It's just because I naturally don't want students working on homework during class. So let me see here. Let me activate 10.5. That's the assignment that's due tomorrow. If you refresh your screen, are you seeing section 10.5? In WebAssign? You have to refresh your WebAssign. Okay, wonderful, Lexi, excellent. Okay, so let me give you till 7:30 to work on that a little bit, take a little break, work on that. And then at 7:30, I'm going to come back and do one more example from section 10.5, and then we'll move into chapter 11. Okay, excellent. I'll stop the recording.